Actually, I didn't want to talk, but it would be curious if we honor Reinhold Bertlmann and don't talk about his work. So I decided I'd talk a little about Bertlmann socks and particle physics, because here he did some really nice works. And I cannot cover everything, of course, because otherwise we would sit here at least until next breakfast. So I will just cover 2 points. So what I will tell you a little bit is about a superposition of particle physics and quantum physics. And what we will do, we will project actually on this superposition, and I hope I can show you that there comes out new physics. And the part 1 will be about Bell inequalities in particle physics, and the next part will be about decoherence and some experiments. Maybe I should also explain why this picture for this program here, and some little history about Reinhold Bertlmann. If you didn't know that, there's a drawing by John Bell. You know, John Bell is, among other things, famous for his Bell inequalities, and I will soon explain what Bell inequalities are. And John Bell had a student, a young student at the time, could say, and this young student had a habit. So if you knew the color of one sock, you know for sure that the other sock is not going to have this color here. So if it would have been pink, then you know for sure that the other one is not going to be pink. So you have some correlation here. And he wrote a paper, you can see it here, Bertlmann socks and the nature of reality. So as you see in the drawing, and if you compare this with the real picture here, you see it's pretty good. Even some years passed, and you all know, I think you all know about the socks, and one can right now see them. So if you know one color,
okay.
And there was a little revenge to the birthday of John Bell, his 60th birthday, drawn by Reinhold himself. So here is a Bell whiskey, and out of this Bell whiskey comes a ghost with 2 different socks. So the color of the socks are different, and some spooky action at distance. This is what Einstein told about all this entanglement stuff I will explain you. And later I had some other revenge. I took the same picture here, and I would put here is a kaon and an anti-kaon. And I will explain to you why I also think that there are spooky action in this system here. Even with not only socks or photons, but also with kaons. Okay, so this picture you have seen already today. So if you look around here, we actually have enough to explain it with 2 quarks, 1 electron, okay, a neutrino, and light. But as you all know, there's more. And so it's obvious that we could ask, for example, because we see this entanglement mainly in this ordinary matter systems or in light systems, we could ask if there is also entanglement in the other system provided by, so the other particles provided by particle physics and antiparticles. And as you can see here already down, you should get the pointer. If I have one. So the pointer works. The research of Reinhold really goes from very experimental, so he proposed experiments which have been already tested in accelerator experiments. We show you some results. On the other hand, from very mathematical aspects. As we learned already in a lecture by Yvette today, that entanglement is defined in mathematical ways, so it's pretty mathematical, but of course there are some physics behind it, but not solved everything. Okay, so as you also know, I think you know, it's only 4% of the universe we know is this standard model described, as we have found out until now, except for the Higgs particle. So, and we assume that there is still some cold dark matter around here and something even more crazy, dark energy. So you see, we still don't know a lot about our universe. Okay, so let's start. So the situation, the famous Einstein-Podolsky-Rosen situation is like this. You have a source producing two particles, and then you have an experimenter Alice and an experimenter Bob. And both of them can do independently some experiments. Here, for example, I have written down it would be a Stern-Gerlach apparatus. So if this would be two spin 1/2 particles, you have here a magnetic field here, and what is interesting on this situation is if Alice and Bob both chooses the same direction, if Alice finds her particle to be spin up, Bob always finds, if he measures in the same direction, spin down, or the other way around. And so how do you explain that? What is puzzling about this situation? And I actually want now to just talk to the people who didn't hear something about Bell inequalities. So who have heard about Bell inequalities? Who have, could if I take him or her out here, really explain what Bell inequalities are? Okay, even less. Okay, so I just want to make this situation. So the experimental situation is like this. If you separate, so we will just make it like these two particles here. Here will be the source, then I will separate these two people here, one particle, the other particle, and then I will, so they are back to back, they cannot see each other, and I will ask them then in 3 different directions. Up, down direction, or forwards, back, right, left direction, and we want to have the same situation as we see in the experiment. So if one has spin up, pointing up in this direction, the other one should go down, if I ask this direction. If one is forwards, the other one should be back. If one is right, the other one should be the other. Okay? Let's try this, if we can do this, if this is a puzzling situation, or if we can solve this situation. So, 2 volunteers, and then a women, for Alice and Bob. Just persons who don't know anything about Bell inequalities. Come on.
So I am still alone.
You. I'm not Alice.
Okay, then I do Alice and you be Bob.
No, I can do Alice. Okay, good. You. Okay, so the situation is, here's the source. You get that separated. You cannot see each other. The audience is not allowed to tell them anything. And then I will ask you one of these 3 directions. And you should always behave in a different way.
And watch.
No, you're not allowed.
Oh my god, it won't work. I'm already
This is a setup.
Okay, the
Sorry.
setup is correct.
But can you talk beforehand?
Beforehand you can talk, but afterwards I have separated you. You cannot talk. Because in the source the 2 particles are together, but if I separate you, you're no longer together. Okay. Okay, there's something going on. Okay, I separate them. So you don't see each other, you don't hear. And I ask you now 1 measurement direction.
Okay.
What is your measurement result? Okay. I ask here. Okay, I think you have to change something.
Yeah.
I've seen it, there was some spooky action.
So maybe the audience who don't know about Bell inequalities are allowed to have them or had. You need some. You need just one measurement per time, you know? If I have a magnetic
You have to
field.
talk.
We should get a quantum team. It's just
So what would be a solution to this situation?
We could communicate.
Yes.
We could call.
Voilà. You could yeah, but you're not to call to each other because in experiments you would need, for example, photons and they are traveling with the speed of light. So
classically correlate.
Yeah.
so you're thinking these swords together.
Okay.
Yes.
I can tell you before where I will put my hand. Well, that's what we try to do.
Okay, but
But
you
I
say
can
okay, so then this would be the solution. We can make it.
That's exactly what we did.
It's the noisy channels, I'm telling you.
Maybe he's a stranger.
So you could maybe do it over the alphabet. So you are always before in the alphabet, so it's up, down. So down would be D before U. This would be one solution.
Okay.
If you could
I
maybe
think it was
remember.
just, I would point backwards, and she would point downwards, and I would point to the right, and she would be opposite.
You
But I'm
remember
not
that?
confused yet.
Okay.
Okay.
Okay, we try it again. Okay, then what
Was ist andere?
Okay, so I asked this direction. Oh! Thank you. Okay, you see, it's nothing puzzling about that. Because, I mean, we solved the situation. It just, these two particles here make it up before. Yeah? If one is up, the other is down. Yeah? But now is, of course, the problem. I mean, how many measurement directions do you have? If you think about spin 1/2 particles and here the Stern-Gerlach apparatus. How many directions are there? 3? Yeah, you cannot choose the obvious one, you can choose any. Yeah, so there are infinite many ways to do that. This means already they have to have a big backpack. So for every direction they have to make up. Yeah? But it would be a solution to this. Okay. And this actually what Einstein called, or in this scenario is called hidden parameters, verborgene Parameter. Okay. So they make it up. And this solves the situation. We cannot actually think about something else because if they are separate, they cannot commute with each other. So how should they actually do that? To behave always the opposite in any direction. Okay. Mathematically, you have seen that already. How such a state looks like. So this is one famous Bell state. This is the antisymmetric state. So for spin 1/2 particles, you would write down spin up for Alice particle on the left side, spin down for Bob particle at the right side, minus spin down for Alice particle, spin up for Bob particle. If you go to quantum information theory, or you think about what is generally called qubits, it's just a two-state system. You would be lazy and just write down 0, 1, 1, 0. We've seen already today something like that. It could be, for example, the ground state and the excited state of the atom or whatever. Or for photons, if you consider the polarization, you would write down horizontal polarized, vertical polarized, and so on. And also in particle physics, you can produce such a state. Here you have a kaon and an antikaon and kaon. So you see here an entanglement between being particle and being antiparticle. This yields the quantum number which is called strangeness. And the same you can also consider for B-meson system. So you would have a B-meson, an anti-B meson, and so on. And even you could formally write down such a state for a single neutron, not two neutrons, a single neutron, going through an interferometer, and you prepare it like this. It goes the upper way, it spin up. If it goes the lower, it spin down. And actually about this you will hear on Sunday by Katharina Dursberger and Yuji Hasegawa. And here you see also some reference Reinhold did, but they will explain you more about the state here. Okay, so we have such an entangled state, and this was this famous Einstein-Podolsky-Rosen criterion, and as we had in this game, we found out we can explain the situation with hidden parameters. And this made Einstein and the two other guys to really say quantum theory is not complete, because there's a zero behind it. Some hidden parameters, hidden because the experimenter cannot see them. Okay? And in more detail, what are Bell inequalities? So you start from 3 or 2 conditions, more or less defined. And then you call this theories which are based on these conditions here, you call local realistic theories. And if you calculate, and this is actually what John Bell did, then you find out that some Bell inequalities where you measure in different directions have to, some probabilities, sorry, where you measure in different directions have to fulfill something like this here. On the other side, you have learned already in the quantum mechanical course, or what quantum mechanics tells you is given the state and what you measure, then you know how to calculate the probabilities. And now it turns out, for all local realistic theories, these inequalities have to be always satisfied. On the other hand, if you insert the quantum mechanical probabilities into these Bell inequalities here, you find sometimes they are violated, they are not satisfied. And this is great, what John Bell in 1964 found, because now for the first time, more philosophical question, if you so want, if there are hidden parameters or not, really you can test that in experiment. So the experiment has to decide whether quantum mechanics is the correct theory or if there are hidden parameters. So the situation, how we can explain this Einstein-Podolsky-Rosen scenario. And there have been a lot of experiments, and because mostly of us are Austrian, I take one experiment by Gregor Weiss. And what he did here, he produced this entangled state here, and here's Alice and here's Bob. And there were already experiments before that in showing that the Bell inequality is violated. What he did here, he tested photons, and while they were flying apart, they really said here what Alice is going to measure and what is Bob to measure, because there was still a loophole there. It's called the locality loophole. It could be like this, that the source somehow knows what Alice and Bob want to measure. And in experiments before, it was like the setting was already given. So Alice and Bob did already decide what they want to measure. And with this experiment, they ruled out why these photons were flying apart. They really said what they are going to measure, Alice and Bob, independently. And still this Bell inequality is violated. So the idea was the nature could be that mean that they really already, so the source already knows how tells the particles how to behave. What is not closed is another loophole. This is called the detection efficiency loophole. It means only a part of the photons are detected. I think about 4%, something like this. 5, even 5, okay, but not a lot. So it could be still that these pairs are created, and just these pairs survive until the detector are detected afterwards, which have this puzzling feature to violate the Bell inequality. Of course, this means, of course, nature would be mean to us, but still it's something you want to test in experiment. And this is not closed by these photon experiments, but it was closed by another experiment with ions. It's this one here. But it didn't close the other loophole, this locality loophole, because they were not separated far enough. Yeah. So until now, there's no experiment closing both loopholes. But still 2 separate experiments. And another experiment with neutrons, but I won't talk a lot about this here. You received by Kati and Yuji's talk on Sunday about that. Okay, let's come back to this neutral kaons. So what are neutral kaons? So I told you already there's a kaon and there's an anti-kaon. And if you look at a kaon beam, you find that for a short while it mainly decays into 2 pions. Then nothing happens and it mainly decays into 3 pions. So this gives rise, there are 2 different mass eigenstates. A short-lived one, Ks, and a long-lived state, K long. So the short-lived state decays earlier than the long-lived state. And it turns out that the strangeness eigenstate being a particle, the K0, is a nearly equal superposition of a short-lived state and a long-lived state. Okay? So that's, you can also think about spin, about that. This would be spin up and this would be another basis. And of course there's a time evolution. So if you look at a kaon in time, so then the short-lived state oscillates with a mass ms and decays with a decay rate gamma s. And the long-lived state oscillates with a mass ml and decays with a decay rate gamma l. And the superposition with a minus sign would just be an anti-kaon. So you see already, if you start with a kaon at time t equals 0, then there's some oscillation. After a while, you can measure anti-kaon. So the probability is no longer 0 that it transformed into another particle. So so there's a kind of strangeness oscillation, starting with a kaon. After a while, it's an anti-kaon, kaon, and so on. And this you call strangeness oscillation, because strangeness is if it's a kaon or an anti-kaon, this property here. And you can also view it in a different way here. It's a kaons are a kind of double slit. So at t equals 0, the slits are equally here, k short and k long. As time goes on, one slit gets smaller compared to the other one because the short-lived component dies out. And of course, after a while, you no longer have kaons, so the whole double slit shrinks. Okay? Okay, so for photons we have such an initial state, and for kaons we have such an initial state. So straightforward, just calculate the probabilities. So the probability to find a horizontal polarized photon in direction n at any side, and a horizontal polarized photon at both sides in direction m is just given by 1 minus the cosine of the angle between these 2 directions. So what you see is if the angle is 0, so they measure in the same direction, the cosine of 0 is 1, 1 minus 1 is 0. So the probability is 0, because if you find on one side a horizontal polarized photon, you find on the other side a vertical polarized photon, like we had before in this situation, with spin up and spin out. So very same. So if you do the same for kaons, everything is more or less the same, except that they have this time evolution, this decaying property. So you end up with this here. And let's do it that way that we set the decay constants to 0. So we got here 1 and here 1. 1 plus 1 is 2, so we can take out a 2. So we have 1/4, 1 minus cosine. Delta m is the mass difference between a short-lived and a long-lived state. And here's the time difference between the 2 measurements Alice and Bob do. And if you compare these 2 formulas, you see already that this time difference here plays the same role as the angle in the photon case. So if they choose the same times, they will find, if Alice finds on one side a kaon, Bob will never find a kaon on the other side. He will find an anti-kaon, or, different to the photon case, a decay product. So in the photon case, if Alice finds a horizontal polarized photon on one side, she knows that on the other side Bob is not going to find a horizontal, but a vertical polarized photon, but it's the same. But in the kaon case, if you find on one side a kaon, you know that the other side is not a kaon, but it means it could be an anti-kaon or a decay product, because they can decay. So there's a little but important difference. And so more generally, what you can measure, and this is what we formulated in 2001, is you have the source here and some measurement device. And it travels a certain distance, this means a certain time. And then you can ask, are you in a certain quasi-spin, Kn, or not? It's important or not. Not only the orthogonal, but it could decay as well, at a certain time Ta. And this is is a very important property, as Reinhold and I found out, because the other people neglected this. They were coming from the photon side, and they did this, and they came into some troubles. I'll tell you a little bit later. So this is what you can generally do. And now the same derivation you can do as for photons, you can do also for kaons. What you have here is this famous Clauser-Reinhold Bell inequality. It's a Bell inequality, but it's a more suited one for experiments. And it looks like this. Here you have the expectation value, so you can always convert it in probabilities if you like. So you have 4 different probabilities. And if you just look at the formula, so what Alice can choose is a certain quasi-spin, so being in a certain superposition of kaon and anti-kaon, like in a spin case. But she can as well choose a certain time, in general, and Bob the same. So generally you could vary in times, choose the quasi-spin and vary in times, or vary in quasi-spin and set, for example, all the time 0, or a certain number, or of course both, just generally. Let's do that. And the first one, which already existed in literature, which was not derived in this general case, but just for a certain choice of quasi-spins, the anti-kaon, almost the anti-time, and just the times varied. And in this case, it turns out that the expectation value is nearly as you expected for photons. So you have here the cosine, here would just be the angle in the photon case, but you have an additional damping function here coming from the decay. And for photons, this Bell inequality gets maximally violated up to 2.8, so 2 times square root of 2. And you see the local realistic series tells you that it has to be lower equal to. So for kaons, obvious, you could do the same and vary in the times, and there was a surprise. You do not find any violation. Whatever for times you choose here, you cannot violate this Bell inequality here. And there were some publications where they actually found a violation of this Bell inequality here. But the problem here was that they didn't take into account that these kaons can decay. But this is a property of this system here, and so to say, the kaons know that they have this decay property, so you have to take this into account. What the other people did they reduce to a subspace of the Hilbert space and tested there the Bell inequality, and there it gets violated. But if you take the whole Hilbert space, as we did and pointed out, it's a subtle point actually, before you find out where is the problem, then you see it's not violated. That's of course not good, because this you could do in an experiment, but it's not even violated in theory, so why do the experiment? Okay. So maybe I should give you a little bit more an idea, so why it cannot be violated. So you have on one hand the strangeness oscillation, so this is the reason why Bell inequality can get violated. And on the other hand you have the decay. And this ratio is about 1 for this neutral kaon system. And if you just choose another one, and we tested if this ratio would be greater than 2, we found out you could violate this Bell inequality here. So the reason somehow is that these kaons oscillate too fast compared to the decay, or they decay too fast compared to the oscillation, as you wish. Okay? So that's the reason. So one solution would be maybe to go to another meson system, and see if it works there, because the other meson system do not have this nice feature of that the decay constants of these 2 different mass eigenstates are different. You have to have that this ratio here has to be even greater 2.6, and you see it doesn't work for the B meson system, it doesn't work for the D meson system. It would work for the BS system, so BS means it has a fringe Fock inside. But the problem here is that you don't even have experimental data here. But another crucial point is, what you need for Bell inequalities is really that Alice and Bob can do active measurement, meaning that they can really decide what they want to measure. And this is only possible for the neutral kaon systems because they live long enough. Long enough in particle physics, in this case, is 10 to minus 10 seconds. That's long for particle physicists. Because this means about some centimeters, of course, depending on this speed, but some centimeters. So there's still something to measure whether it's a k-short, a kaon or an anti-kaon. You just put there a piece of material there, and you need this. This needs to be at least some micrometers, and this you cannot do for this meson here, because they simply do not live long enough for that. So the only system where you can really, or may really test Bell inequalities, I should say, is this neutral kaon system. But as I told you, whatever you choose here, it doesn't work. Okay, so we have to do something else. We have to be more tricky. And for that, let us go back in the year 1964. That's a famous year because here John Bell found these Bell inequalities. On the other hand, it was also a really interesting and surprising year for particle physics because they found the so-called CP violation. CP violation means, you know, we have a word with particles and we have an anti-word with antiparticles. And until 1964, the people thought, okay, if we interchange all particles here in the room with antiparticles, it would be the same universe, the same natures. But that's not true. Actually, there is a small, but there is a difference between the word of matter and the word of antimatter. This is called CP violation. And this was actually found in this neutral kaon system for the first time. So, how is it? Both the kaon state as the anti-kaon states, both can decay into 2 pions or into 3 pions. 2 pions turns out to be a CP plus state and 3 pions is a CP minus state. So C is a transformation which takes from a particle to an antiparticle, and P is the parity. Okay. This you find out if you study all the reactions of these particles. And what they found out in their experiment is that after a short while, as I told you, they decay mainly into 2 pions, but after a long while they decay mainly into 3 pions, but sometimes you see also an event of 2 pions. And 2 pions is a CP minus state. So in our language, it means that a short-lived state is mainly a CP plus state, a K1, but is superposed a little bit of a CP minus state. Okay, this epsilon is really small, it's about in the order of 10 to minus 3. Okay, so there is not a huge symmetry violation, but a small one. There's a small difference between it. And you can see those in another quantity if you wait long enough or take a reaction where you can produce just a long-lived state, then it decays mainly in a positive. So it decays in a semi-electronic decay mode, meaning that you have here lepton, either being an electron or muon. It can be positive charged or negative charged, and if the symmetry was conserved, this needs to be 0. But it turns out it's not 0, it's 10 to minus 3. And actually this CP violation could, in principle, explain why we are living in a world or a universe where we mainly see matter around us. So if we even look at the galaxy, it's matter and not antimatter. If the matter has some advantage a little bit, if we consider the Big Bang and matter and antimatter was produced in the same amount, and if matter has a little bit advantage, then it could be because matter and antimatter annihilates. We could explain why we live in such a universe where we simply see only matter. But this effect is too small. If our theories about the Big Bang are correct, it turns out that this is actually too small. So it's a still open question in particle physics. Okay, but come back to Bell inequalities. So what we do, we take this general one and choose the variant the quasi-spin. And if we do another trick we found out, then we can actually find that this delta needs to be lower equal to 0. So this is the Bell inequality. For simplicity, we took all times equal to 0 and chose this quasi-spin 0. And this delta is simply this value which is measured for single kaons, even not entangled kaons. It's found to be 10 to minus 3. So if you compare these two here, you see a contradiction. The Bell inequality is violated because this is positive and this tells you it should be negative or 0. Okay? So somehow we have done now something really puzzling. So we have connected two different concepts. One in particle physics, the symmetry concept, which is very powerful there to use, and the violation of a symmetry. And on the other hand, entanglement or non-locality. So if a state violates a Bell inequality, you may call it non-local. Okay? Because this is more the feature we think, which is tested by that. And I can even make it stronger. If I take another Bell inequality, I just chose here a kaon, then I get this Bell inequality, and if I put this together, it really means that delta should be equal 0. So it means really if I want to describe this neutral kaon system by a local realistic system, I cannot include CP violation. Because Bell inequality requires, or local realistic zeros require really delta to be equal 0. Okay. Good. So now we have proven somehow that Bell inequalities are violated. So this neutral kaon system behaves as crazy. So what we cannot explain, like we did in this game, they didn't make it up, because this would mean that the Bell inequalities have to be satisfied. Okay. So there's really some spooky action going on here, as Einstein called it. We saw this also for this neutral kaon system, a really strange system. Not the usual, you could say in ordinary matter you find it, in light you find it, but maybe you wouldn't mean that it doesn't mean that it's a general feature. But it turns out you find it even in such exotic systems here. But the bad thing about this Bell inequality here is that you can never do a direct experimental test. I mean, if you believe that you know that the state is this entangled state in the beginning and you know how you calculate the probabilities, then you end up with this here. But you cannot do the experiment because you cannot distinguish between a short-lived state and a CP plus state. Okay. So you cannot do it directly, and that's of course not nice, because we would like to really have an experiment where we can test this feature, if it's really there. So we are thinking about that for many years, and this was, as I told you already, it's not violated, but you could do this in experiments. And when we consider these things, I showed you that these kaons are kind of double-sleeved, evolving in time. But if you have a closer look at this here, what you find out is if t is not equal 0, it's not normalized. This is something you didn't see in the basic courses. Or if you had to normalize it. Okay? So you had to find out what to write down here. And this is something not what you're used to, and actually it means you can describe this decay property so that you lose kaons with a different idea model, which is very famous now in a different field. It's called decoherence. So the idea is like you have your quantum system, but it's not isolated. You never will really be able to isolate your quantum system fully. So you have some environment around it. And there are some interaction with the system you are interested in and with the environment. And this causes, whenever you maybe even start with a pure state, that after a while it will get mixed, because the environment somehow measures some degrees of this quantum system. So this is what you call decoherence. And what we found out is that this decay property of this neutral kaon system you can describe or view as decoherence. So you start with a pure state, but due to this decay property, it's like an interaction with an environment, whatever, QCD vacuum, whatever. You don't need to model it because you can just simply put here in these operators the effect of this interaction. And you see that it gets more and more mixed. Okay. And from decoherence studies, we know somehow if you have that there are some systems which are more robust against this interaction with the environment, more robust against this decoherence than other systems. Some decohere very fast, some slowly. And this gave me the idea it may be worth to think about another state, just a general state, not this spin singlet state, which you can produce in accelerator experiments, but just take a general one and really calculate the expectation value. And you see already it's pretty complicated. It's straightforward. Everyone here in the room could do that, because given the initial state, given what you measure, you can derive this expectation value. It's just no fun to do that. And actually, little exercise we do just, if you don't allow these kaons to decay, so set all this to 0, you just end up with these two terms here you would have in a photon case. Yeah? Or the other ones would be simply 0. Okay. It's straightforward, but nobody did it before because nobody said it's worth doing that. Yeah? And then there was a surprise that indeed, then you have numerically to optimize over that. So it's also not fun because you have one expectation, you have 4 different of that, and then you have to optimize over them. Yeah, it works still with Mathematica, so it's not a really hard problem, but it's, I would say, also not fun. Okay, but anyway, the result was something nice. Indeed, so this was the initial state this Spinks linear I showed you, which is not violated for some parameters of the time. But indeed, there is a state which violates the Bell inequality. Not a lot, so maximum 2.1, but still above 2. That's enough. If there is a violation, then you have proven that you cannot make it up before. There is no backpack carried by these particles, explaining that. And there's also another state which would be more suited for experiments, of course. It's not that high, but it's for longer times. So now it's good because this is the duty of a theoretician, find something that people can test in experiments. We found a violation, so now they could do the experiment. However, the problem is how to produce this initial state. This is still open. We are working on that. So I'm working with Antonio Di Domenico in Frascati. Catalina knows him well on this here. He's very much interested in this stuff. And we're trying to somehow produce this state. And what is interesting also from the theoretical part here, this is not the maximally entangled state as you would suppose, because you would say, so for qubits or photons, it's the maximally entangled state maximally violates the Bell inequality. But here it turns out a non-maximally entangled state violates the Bell inequality maximally. So there is no one-to-one correspondence between this, what I would call non-locality, tested by Bell inequalities, and the other entanglement, which is what we defined today pretty mathematically on the states in angular space. Okay, so much to that. So I will go to another topic which we did at the same time we were started with. Another idea is, okay, fine, you produce this spin singlet state, this accelerator experiments, and I show you soon one. And Alice and Bob do their measurements, or the decay, we can think about these things. But there may be some interaction with the environment. So some real decoherence, not the decoherence coming down from the decay property, some real interactions with the environment. And could you test that in experiments? And this was actually my diploma thesis given by Reinhold when I started. So in 1998, there was an experiment. In the last days of this experiment, the CPU experiment, they did some experiment to this quantum feature. I maybe should tell you that it's really crazy because at the time Reinhold started, it was like in particle physics, John Bell asking people always if they were interested in this quantum stuff, and where also Reinhold first got to know about it, if they have a permanent position, because you shouldn't start doing that kind of physics if you don't have a permanent position, because it was thought to be something strange, weird, not productive. And at that time, so and now, of course, you know, a new field emerged, quantum vision, quantum computer, quantum cryptography, and everything like this. And now somehow we try to get somehow back, so to test really quantum mechanics within particle physics. And so this was one experiment done in this, and there are actually not that many. So what they did here is they produced such a pair, maximally entangled pairs in singlet state, and then they had here some material and here some material. So this was just 2 centimeters, and this here is 7 centimeters. So you have two situations. If it's produced within this angle here, then the kaons travel both the same distance, so the same time they are measured. So if you find on one side a kaon, on the other side should not be a kaon. Or you have another situation, a second one, where one is 2 centimeters and the other one is 7, so the difference is 5 centimeters. So there you should see some different behavior. So this asymmetry term is defined depending on this time difference. Is just defined as the probability to find unlike, so Alice finds a kaon, Bob an anti-kaon, or vice versa, minus the probability that they find the same strangeness. Okay. So if you derive that, it's simply this cosine, so giving the strangeness oscillation and the damping function coming from the decay. And here you see the experiment. So actually you should just look to the right, because if you have minus 5 centimeters or 5 centimeters, it's the same, it's just a time difference. And they have 2 measurement points. And here they have the curve, what they called quantum mechanical curve. So it's already a corrected one, or the experimental data is corrected to that. And in this paper here, they said that quantum mechanics is confirmed by this experiment here. I would say through 2 measurement points I can have a line, some other curve, whatever. Yeah? To say, okay, it really confirms quantum mechanics with 2 measurement points is maybe not the best one. So this is what Reinhold asked me. So how good do these 2 data points really verify this quantum mechanical interference term, so this cosine? Then they also stated in this paper, and I will explain you in a minute, that the Schrödinger-Furry hypothesis is ruled out in this experiment here. And as I told you already, some motivation is to find out if there is some decoherence in this system, some interaction with the environment. And so what is Schrödinger-Furry's hypothesis? It goes actually back to Schrödinger first, 1935, so pretty early, the beginning of quantum mechanics. And Furry also considered that. So the idea was like, okay, we produce this maximally entangled state in the beginning. So I have written down it now in the short and long-lived basis. In quantum mechanics, I can choose any basis I want. So K short, K long, minus K long, K short. And the idea was, okay, this is at t equals 0, this is produced. But if they separate, it spontaneously factorizes in a separable state, the short-lived state at the left and the long-lived state at the right, or vice versa. Okay? This would of course mean that there is no interference term. And we modified this a little bit. So as you know, if you have such an initial state and then you project onto that what you want to measure, so you have 2 different amplitudes, one coming from here and one from here, and a minus sign, and you have to take the square of it. So it means any probability is the first amplitude squared plus the second one minus 2 times the real part of the first complex conjugated in the other one. This is what you did in the problem solving courses. And what we did now, we just put in here by hand a 1 minus theta. So if theta equal 1, then it's actually this situation here. You have no interference term here. This is also, if you think about the double slit experiment, this would be actually if you see no interference. Okay. And now then we put all these probabilities here in this asymmetry term which was measured in this experiment. And it turns just out this is just the one without, if theta is 0, and modified by 1 minus theta. And now was the question to ask how big can this theta be? From the experimental data. And okay, but there's another way, because in quantum mechanics I can write down the state in any basis I want to. So I could also write it down in the strangeness basis, kaon, anti-kaon, anti-kaon, kaon, and ask the same question. Okay, it's spontaneous effect raises in a kaon at the left and an anti-kaon at the right, or vice versa. A totally different situation, of course. Yeah. And if I do that, the same idea, I just put here 1 minus cetus, then I end up with this term here. And you see it's already more complicated than before. So you see you have not only the time difference here, but also the sum gets into that, and more complicated. But this would be, of course, also a situation I could consider. And then we compared it with the experiment. And this was our result from the CPD experiment. With these 2 data points, we found out if we think about this decoherence happening in this k short, k long basis, then theta could be up to 0.2 still. And of course 0 is included, the quantum mechanical result. On the other hand, if you think about a decoherence happening in a k0, k0 bar basis, then you see theta equal 1 is not excluded at all. Okay, so this would be possible. This is not ruled out by the experiment. So this situation could happen. And until that, I showed you already Antonio Di Domenico did some studies for K-mesons, not at the CERN experiment, but there is another experiment in Frascati. There is an accelerator, E plus E minus, electron-positron machine, and they actually produce a phi meson and this decays into 2 pions, 2 kaons, 2 entangled kaons. And he did the same, so, and of course he is experimental, so he gets even more. He gets not only 1 error, but 2 different. One is statistical and the systematic error, and he found this value here, so pretty close to 0. So decoherence is not a lot in this system. And the same, and a very good value, 10 to minus 5, he found for the other bases. But one should say here, what he measured was, in the CPD experiment, you measured whether it's a kaon or anti-kaon. In this here, you use some decay modes, and you measure somehow it's a k short or k long. So it's actually a different situation. But if you assume the situation is the same, then you can compare that. And later we did also some more studies with more statistics, and you see these values here. Yeah. But actually this theta here is really just a factor we get there by hand, which gives you some intuition how good this interference term is. But of course we would be more interested, because if we learn something about all these Bell studies, is that this system, you cannot separate it. You cannot say there are 2 different particles. They belong together, they are entangled. So the idea is that if they are entangled, they also interact with the environment together, not separately. And some people proposed, for example, that decoherence happens, that one kaon interacts with the environment, the other kaon also interacts with the environment. And this would give them some 1 minus e to the minus lambda. Lambda would be the interaction, and the sum of the two times. But what we think is really, what one learns is that the state is entangled, so it's one, you have to consider it as one system, not 2 separated particles, and it would interact with the environment together, and then it would be just 1 e to the minus lambda t, with t being the first measured kaon. Okay, because after one is measured, the entangled state is destroyed. The other one is separated. Okay? And so all these things, you can test them, and it was also done for B-mesons, some old work by Bertlmann and Walter Demos on B-mesons. And also Gerhard Richter did his PhD on that with B-mesons and tried to find out this time dependence, because the theta doesn't take any time dependence, so it's integrated over all times. Okay. So this is what we really want to find out, but unfortunately couldn't really find out some lambda because of some experimental details. Okay, I think you are tired enough already. So I just want to tell you that there is a lot to do. So I hope I could show you a little bit what Reinhold was doing, so some superposition of or some testing of quantum mechanical foundations in system of high energy physics. I show you a little bit about Bell inequalities. So the story is not yet ended. We don't yet have an experiment. There are still some other features we could think about that. Then there's another one, a little bit I told you about decoherence, but it's also connected to entanglement measures. Actually, one basis for the people who know it, the theta parameter would just be Rooter's concurrence. You can find that, but you can do also some other crazy stuff. You may have heard about quantum erasers. These are Quantenradier in German. So it means some quantum marking and erasing. Some crazy idea like we know that photons can interfere through a double slit. We know if we close one slit, they do not interfere, we see no interference. But on the other hand, if you put there someone watching the photon, we know that the interference pitch is destroyed because we gain which slit information. It took the upper slit or the lower slit. But if this other system is a quantum system and we erase later the information out of it, we can regain interference. And this is really crazy. It was found out in 1982 by Dröll and Scully. Okay, and this is called quantum marking and eraser, Quantenradier in German. And with kaons it's interesting because you can do the same stuff as you can do with photons or atoms, but you can do even more. And the reason for that is because for kaons you have some active measurements, which is important for Bell inequalities, that you really, Alice decides, I want to measure that, or Bob decides. But on the other hand, you can just wait and see for a decay product, and this tells you also whether it was a kaon, an anti-kaon, or k short or k long. So you have a fully passive measurement device as well. And this you can take, and then you get more options than you get for photons. So I think this somehow shows nicely that there is more if you study such kind of systems than you can learn from ordinary matter and light. And some other stuff you can do here as well. Okay, so thank you very much. This is the group before we enter the double slit. You see what happened afterwards, but unfortunately we don't remember how it was going through the double slit. Okay, are there some questions? Or did I confuse you fully?
Yes, I have a question.
Yeah.
You mentioned the CP violation and this parameter epsilon, and that it was too small to explain the imbalance of matter and antimatter we see today. But might it possibly be that for other particles, not K-mesons, this parameter would be different? So that would
Yes. So that's a good point. There are many different CP violations. So this is, for example, CP violation mixing. But there's also some direct CP violation even in the kaon system. And CP violation is also found in the p-meson system. But still, it's just even smaller. It's 10 to minus 6. So, yeah. So still this is open. But of course, you can always question if we have a really good model about Big Bang. And of course, particle physics usually say that they know up to 10 to minus 30 seconds what happened. Yeah. Okay. If not, then we will have about 5 minutes break, and then we will start with a little feature. First, we will say something, and then we start with a feature. Okay.